Hello and good morning to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will discuss another important problem in process synchronization that is called as dining philosopher's problem. Dining philosopher's problem states that there are five philosophers seated around a circular table with a bowl of food before them. Placed around the table are five chopsticks. These chopsticks will be used by philosophers in order to perform eat operation. There are two operations defined on the philosophers. The philosophers can either eat or they can either think. In order to facilitate eat operation, a philosopher should have control over two chopsticks that are closest to it. Otherwise, a philosopher needs to perform think operation. So here the problem is to synchronize eating and thinking operation of five philosophers seated around the table. So this is what dining philosophers problem is all about. So let us try to understand the problem in detail. The problem states that there are five philosophers sharing a circular table. The activity that a philosopher performs is eat and think alternatively. So, a philosopher can perform eat or think operation. There is a bowl of food for each of the philosophers and five chopsticks around the table placed in between the philosophers. So, in order to enable philosophers to eat. A philosopher needs both their right and left chopstick to eat. So a philosopher should grab or have a hold on both right and left chopstick in order to perform or in order to enable a philosopher to perform eating operation. A hungry philosopher may eat only if there are both chopsticks available. Otherwise, a philosopher puts down their chopstick and begins thinking again. So this is a very simple description of dining philosopher's problem. Now let us go through some of the important impositions on dining philosopher's problem. The first imposition is that when a philosopher thinks, he does not talk to others. So this is the first imposition that dining philosopher problem has in it. When a philosopher thinks, he does not talk to others. When a philosopher becomes hungry, he picks up the two closest forks or chopsticks. A philosopher can pick up only one fork or a chopstick at a given point in time. He cannot pick the chopstick or a fork which is in someone other's hand. So he cannot pick the fork or chopstick which is in other philosopher's hand. When a philosopher gets both the fork or chopstick, he starts eating without releasing it. When a philosopher finishes eating, he then releases both the forks and starts thinking again. So these are some of the important impositions on dining philosopher's problem. So when a philosopher thinks, he does not talk to others. When a philosopher becomes hungry, he picks up the two closest forks. A philosopher can pick up only one fork at a time. He cannot pick the fork which is in someone else's hand. When a philosopher gets when a philosopher becomes hungry, he gets both the forks, he starts eating without releasing it. When a philosopher finishes eating, he then releases both the forks and starts thinking again. So these are some of the important impositions on dining philosopher's problem. Now let us formulate a strategy for the same. The strategy is to first represent each of the chopstick by semaphore, because as we have learned that a semaphore, a chopstick needs to be available in order to enable a philosopher to perform eat operation. So here we will be representing each of the chopstick or the fork with the help of a semaphore. A philosopher takes hold of a chopstick by executing wait on the semaphore. So we have already learned wait and signal operation that can be performed on semaphore. So wait decreases the value of semaphore, whereas signal increments the value of semaphore. Wait performs operation when the value of semaphore is greater than 0. So a philosopher takes hold of the chopstick by executing wait on the semaphore, right? Likewise, a philosopher releases the chopstick by executing signal on the semaphore. So wait and signal is used in order to enable philosopher to perform uh, to 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 grab hold of the chopstick and to release the chopstick respectively. Here we need to implement semaphore as an array of semaphore variables because there are 5 chopsticks. So here we will be requiring an array representing semaphore, right? Array representing semaphore. So we have array of chopsticks. So since we have 5 chopsticks, so we'll have an array of size 5. So we need array of semaphores. So semaphore chopsticks 5. So here, since there are 5 chopsticks, that's the reason why we have used an array. Now, the initial value of all the chopsticks will be 1 because initially all the chopsticks are free. So initial value of all the chopsticks will be 1. So these are the set of the strategies that we will be trying to pursue in order to uh, resolve or help philosophers eat or perform eat operations. So here each chopstick is represented by semaphore. So a philosopher takes hold of a chopstick by executing a wait on semaphore. A philosopher releases the chopstick by executing signal on semaphore. We need an array because there are 5 chopsticks that are available and all the values or the initial values of all the chopsticks will be 1. Now, this is a very simple implementation of the dining philosopher's problem. So here, what I'll do is, in order to enable, philosopher eat, so I need to ensure, so this is a very simple orientation of the 5 philosophers, right? Okay, so we have philosopher 1 to 5 and we have chopsticks 1 to 5. So here, first, what I'll do is I'll implement a wait on chopstick I. So here, let us consider philosopher 1. So philosopher 1 first implements wait on CS1, that is chopstick 1. So initial value of chopstick 1 is 1, so it will be decremented by 1. Then it will implement a wait on chopstick of I plus 1 mod 5 because since there are 5 chopsticks, so I plus 1 is 1 plus 1 is 2, so 2 mod 5 is 2, so chopstick number 2, so it will implement a wait on chopstick number 2. So since CS2 has initial value as 1, so it will implement a wait on chopstick 2, so then P1 will be able to eat food using chopstick 1 and chopstick 2. So first what it will do, it will pick up its left chopstick, that is CS1, and then it will pick up its right chopstick, that is CS2, and it will perform eat operation. So that is the way how the implementation of dining philosopher's problem is done. So first it will implement a wait on chopstick I, right? Then it will implement a wait on chopstick I plus 1 mod 5 because there are 5 chopsticks that are there on the table and it has to be the nearest one, so it will be I and I plus 1, right? So now why I plus 1 mod 5? There might be a question that why not I plus 1 and why I plus 1 mod 5? Because if you consider the fifth philosopher, so fifth philosopher will pick up what? Fifth philosopher will pick up chopstick number 5. So it will implement a wait on chopstick I. So that is, it will implement a wait on chopstick number 5. And then it has to implement a wait on chopstick number 1. So chopstick number 1 will be 5 plus 1 mod 5. So 5 plus 1 is 6. So 6 mod 5 is 1. So that is the reason why we are setting it as I plus 1 mod 5. Because I need to facilitate all the philosophers to pick up the chopstick. So for philosopher number 5, it will be chopstick number CS5 and CS1. So in order to facilitate it to pick CS1, so we are making it I plus 1 mod 5. So that is the reason why it's I plus set to I plus 1 mod 5. So a philosopher will implement a weight on chopstick number I, and then it will implement a weight on chopstick number I plus 1 mod 5. So for process 1, for philosopher 1, it will be CS1 and CS2. For philosopher 2, it will be CS2 and CS3. For philosopher 3, it will be CS3, CS4. For philosopher 4, it will be CS4, CS5. And for philosopher 5, it will be CS5 and CS1. So once a access or exclusive access is given to a particular philosopher to have both the chopstick, then the philosopher can eat. And then once the philosopher eats the food or completes the eating process, then it will execute a signal on chopstick I and execute a signal on chopstick I plus 1 mod 5, because it has to release both the chopstick, and then it can perform thinking operation again. So this is the way how a dining philosopher's problem is implemented. So first it will execute a wait on chopstick I. It will execute a wait on chopstick I plus 1 mod 5. So we have understood why it's I plus 1 mod 5, because I need to facilitate philosopher number 5 to pick up CS5 and CS1, right? So if a philosopher has privilege to both has been granted privilege to both the chopstick, then the philosopher can eat, and then a signal is executed both on chopstick I and I plus 1 mod 5 in order to release the chopstick, and then the philosopher will think again. So these are the sequence of steps that are followed in order to synchronize action of various philosophers. Now, there are some identified problems with the proposed solution. The first problem is, although no two philosophers are eating simultaneously, it does not ensure that there will be no deadlock. Right? So just see, this point is to be understood carefully. Although no two philosophers are eating simultaneously, it does not ensure that there will be a deadlock. Let us consider a situation. Let us consider all 5 philosophers get hungry at the same time. So what they will do, they will pick up all of them will pick up their left chopsticks and then try to pick up the right chopsticks. Now, since the chopsticks that are there at the right of the philosopher may be the chopsticks that are placed onto the left of the other philosopher. So all the philosophers will pick up their left chopsticks. So if all the philosopher picks up their left chopsticks, then there are no vacant chopsticks on the table that can be picked up by any of the philosopher. So this is a typical problem that is there with dining philosophers problem, right? So therefore all the philosophers will be delayed forever, right? So here we have considered a typical example where the situation of deadlock arises because all the philosopher falls hungry at the same point in time, and all of them picks up their left chopsticks and waits for the right chopstick that has already been picked. So this will definitely lead to infinite delay in the eating process of the 5 philosophers. So this is a typical problem that's associated with dining philosophers problem. Now here what we have done is, if you can recall and think over this particular solution. So what we have done is we have used a very symmetric solution. Symmetric solution is that we are allowing philosophers to pick their left chopstick and then their right chopstick, right? Okay, so we are using a very symmetric solution. So a possible key to this may be, or possible way to come out of this particular problem may be, you can allow at most 4 philosophers to dine instead of 5, right? So at most you can allow 4 philosophers to dine instead of 5. So here, if 4 philosophers are allowed to dine, then you will have 1 extra chopstick. So even if all the 4 philosopher picks up their left chopstick, so there will be 1 chopstick that will be left on the table, that will enable at least one philosopher to complete each operation. So then consequently the other philosophers can perform their eat operation as well. So this is one potential solution that you can use. So allow at most 4 philosophers to dine instead of 5. Second possible solution may be allow a philosopher to pick up the chopsticks only when both are available. So this may be a potential solution to this particular problem. So allow a philosopher to pick up the chopsticks only when both are available. So even if when one is available, a philosopher should look for whether the other one is available. Only if both are available, then they should be allowed to pick up the chopstick. Or instead you can use a very asymmetric solution. So in the former pursuit we had used a symmetric solution. We can also use a asymmetric solution. That means different solutions for different sets of philosophers that are there in the philosopher set. So first what I can do is I can one of the ways can be I can partition the philosophers into two sets, the odd set and the even set. For odd set, the philosophers will first pick up their left chopstick and then right. And for even set, they will pick up their right chopstick and then the left. So in this way, what we can do is we can resolve the problem that the problem of deadlock that we had identified, right? So these are potential way outs in case of dining philosophers problem. So here we have learned that possible solutions to the problem of deadlock may be at most 4 philosophers may be allowed to dine instead of 5, so that one chopsticks left on the table, so that at least one completes. Consequently, others will also complete. Allow the philosophers to pick up the chopsticks only when both the chopsticks are free, or use a symmetric solution instead of symmetric solution, where we propose different solutions for different types of or different subsets of the philosopher set, wherein the odd set will be picking up their left chopstick and then their right chopstick, whereas the even philosophers or philosophers from the even set will be picking up their right chopstick and then their left chopstick. So in this particular class, we have learned about what is dining philosopher's problem, right? Okay, what does the problem state? Okay, we have learned about what are the impositions on dining philosopher's problem, right? We have learned various impositions that are there on dining philosopher's problem, and then we have formulated a very simple strategy, and we have created a description of the weight and signal over the various chopsticks that are there in order to facilitate philosophers to perform eat operation. Then we have identified some notable problems with the proposed solution. Okay, the problem of deadlock, and then we have also proposed possible way outs for avoiding the deadlocks, where we have proposed that at most only 4 philosophers may dine instead of 5, or allow philosophers to pick up the chopsticks only when both the chopsticks are available, or use a asymmetric solution instead of symmetric solution, wherein you impose different types of solution for different subsets of philosophers that are there in the philosopher set, where we have proposed for for odd set philosophers will pick up the left chopstick and then the right chopstick, and for philosophers belonging to even set, we'll first pick up the right chopstick and then the left chopstick. So this is what dining philosophers problem is all about. Thank you very much. Have a very nice day.